So in this part of the lecture, we will discuss the concept of measure spaces. So, but before that, let me discuss what is a measure space in a nutshell. So a measure space consists of three parts. The first part would be the ambient space, where the objects or the points are located. The second component would be the collection of portions of this ambient space. And the third component is what we call the numerical measure. So the ambient space, the collection of portions of the ambient space, and the numerical measure would comprise what we call a measure space. For the numerical measure, you can think of, let's say, geometric quantities such as length, area, or volume. You can talk about also the cardinality or the number of elements. And in terms of physical quantities, you can think of a mass, for instance. The appropriate mathematical objects that would describe these three components are the following. So here, the ambient space will be modeled to be a set, and the collection of portions would be collection of subsets of the set corresponding to the ambient space. And this numerical measure would be a function acting on the collection of subsets. Of course, we want that the function to be non-negative to make sense, for instance, in this case of this example, because you cannot have a non-negative cardinality, a non-negative length, etc. Well, this is abstract at this point, but let us give a more intuitive example. Counting marbles. Okay. So here, suppose that we have a collection of marbles denoted by M. Okay. And then let us take two portions of this set M. So M here would be your ambient space. Okay. And here we have two portions, R and B. Okay. R denotes for the red marbles and B for the blue marbles. Well, the common to them are the violet ones. Okay, so let us agree that here the measure would be the cardinality or the number of sets. So this example, the number of elements of the red marbles, including the violet ones, are 7. So it's 1, 2, 3, 4, 5, 6, 7. Okay. On the other hand, for the blue marbles, including the violet ones, we have 1, 2, 3, 4, 5, 6. So the number of elements is 6. Okay, so here we can count these two portions, R and B. So if we can count the collections R and B, then one could also, in principle, compute the number of elements of the combination, the elements common to the two sets. And if you cut one set from the other. For instance, here, if I have this set R and I cut the portion of B, then I'll end up with this region. So in terms of set operations, so this would the combination correspond to the union. The common elements would correspond to the intersection, and cutting would be associated to the set difference. So what we are saying here is that if we can count the red marbles and the blue marbles, including the violet ones, of course, then we should be able to compute the common marbles, the combination of the set of marbles, and then the number of marbles by excluding or cutting the blue marbles, for instance. So how do we do that? Well, one could compute the common to the two set of marbles. In this case, those are the violet ones. In here we have two. Okay. Once we know the number of elements common to the two set, a basic accounting principle tells us that if I want to compute the combination, or more precisely the union, what we do is we count the number of elements in each set and then subtract the intersection, because this portion has been counted twice, one as part of A and the other as part of B. Okay, so we need to subtract the number of elements in the intersection. So that would be 7 plus 6 minus 2, and that would be, oops, I apologize for that. Presentation mode, okay, and that would be 11. Okay. Now, on the other hand, if I want to compute the number of marbles, if I cut the set B from the set R, so this would be the set difference. So what you do is you take the set R, but instead of subtracting the number of elements of B, because the blue ones here does not belong to R, it's suffices to subtract the elements common to R and B. And again, those are the violet ones. So that would be 7 minus 2, and you get a 5. Okay. So based on this example, so this collection should satisfy some properties involving set operations. Okay. So in the counting marbles example provided here, if we can count the number of elements of two sets, we should be able to, at least in principle, take the number of elements of the union, the intersection, and the set difference. So for this lecture, we will discuss classes or collection of subsets of a given set, taking into account these operations that we would like to consider. Okay, so let us discuss rings and algebras. So suppose that X is a set and R is a subcollection of the power set of X. So what is the power set of X? Recall that the power set of X is the set of all subsets of a given set. Let's say in this case X. Okay, so this collection R will be called a ring, provided that the following three properties are satisfied. Okay. 1, the empty set must be in R. If I have two elements in R, then the difference must be in R. And finally, the union of two elements in R is also in R. Okay. So again, a collection of subsets of X is a ring if the empty set belongs to R, if the collection is closed under set difference, and if it is closed under uh, the operation union. Okay. Well, in the case of counting marbles, uh, this just means that if you have an empty collection, then of course the number of marbles or the cardinality of that set is a 0. So we want this case as well. Difference, as we have seen, is the one cutting one set into another set. And the union is the combination of the two sets. Okay. So here we have three properties wherein the intersection was excluded. However, one could show that the intersection of two elements in a ring is also an element of the ring. Okay, and how do we prove that? Okay, well, during this lecture, we will not provide rigorous proofs of equality of sets, but instead we will use Venn diagrams to illustrate how the sets are equal, and you can later prove the equality of sets just by using, let's say, by using an algebraic method or what we call a pick-a-point method and the double set inclusion. Okay, so here we'll provide justifications using Venn diagrams just to have a better intuition of the equality of sets that will be presented in this lecture. Okay, so consider two sets A and B. Okay, and this shaded region here is the intersection. Now, if we take the difference of A and B, more precisely A minus B, that would be the red shaded region in this case. Okay. Now, if you take A and then subtract this region here, okay, you will get this green shaded region. This means that A minus B is the same as the intersection of A and B. Okay. So if these two are equal, and we know that a ring is closed under the operation of taking or the operation set difference, then this must be in R. So therefore, the intersection must be also in R. So in other words, we just need to apply R2 twice to show that or to say that this difference is in R. Okay. So therefore, the intersection of two elements in a ring is also in a ring. So in this way, we can also say that a ring is closed under intersections, finite intersections to be precise. And in fact, if you have a finite list of elements in the ring, then the union as well as the intersection of these sets is also in the ring R. Well, for the case of union, you just need to apply R3 and the principle of mathematical induction. Okay. And for the case of intersection, you apply the first remark, more precisely this one here, and apply as well the principle of mathematical induction. Okay. So the details are left for you to check. Well, a ring is also closed under the operation symmetric difference. So what is the symmetric difference? So the symmetric difference of two sets A and B, denoted by A triangle B, or delta for the Greek letter D, denoting difference, is the union of the set difference A minus B and B minus A. So an alternative formula would be the symmetric difference is nothing but the difference of the union and the intersection. And this would be the union of the shaded regions here, the one in red and the one in blue. Well, the symmetric difference, term symmetric, comes from the fact that we can interchange the order of the sets here. So if you interchange A and B, in other words, these sets will interchange, and you know that unions are commutative. Therefore, the symmetric difference, the order of sets in a symmetric difference is not important. Okay. Now, we say that the symmetric difference is also in a ring. Well, you could already see it here because the operations involved are just taking unions and taking the set difference. And if we recall the definition of a ring, okay, R2 and R3 tells us that a ring is closed under the set, the operations set difference and set union. Okay. Well, if you want to be more precise, this should be in R by R3, R2, I should say. This is also R in R, again due to R2, and then therefore the union of two elements in R is also in R due to R3. Okay. So that's the long way. But again, as I said, the shorter way is you just need to check or see the operations involved. They are just unions and intersections. And since a ring is closed with respect to those operations, then this set here must be also in a ring. Some of you might have taken an abstract algebra course, and there is a definition of a ring in that case. Okay. So in algebra, you basically have, for instance, in the case of ring, two operations, usually denoted by what? Plus and the notation for a multiplication. Well, if you have a ring, in the sense of the previous definition, together with the operations, the symmetric difference, as well as the intersection, then this triple will be a commutative ring in the algebraic sense. So this means that our definition of a ring is the same with the appropriate notion of addition and multiplication, okay, for sets. So the verification of this remark will be provided in your first exercise. Now, there is what we call an algebra. So an algebra on a set X is a ring that contains the set X itself. Take note that a ring might or might not contain the set X. However, if a ring contains the whole set X, then we call that ring an algebra. Okay, so an algebra is a ring, but not the other way around. So to prove that a collection of sets is an algebra, well, the first definition would be what? To prove that it is a ring. In other words, you want to verify these three properties, R1, R2, R3, and then show that X must be in the collection. Okay. However, the following proposition tells us that one could verify these three properties, A1, A2, A3, and this would be equivalent in showing that a collection is an algebra. So I have an algebra A on X if and only if these three properties are satisfied. Okay. The first one, X must be in the algebra. Of course, that is by definition. It must be closed under complementation. So here we need to take the complement with respect to the set where the algebra is taken into account. So here we have an algebra on X, therefore the complement must be taken with respect to X. So you think of X as your universal set. So that's A2. Well, this comes from the fact that X is in A and a ring, an algebra which is also a ring, is closed under the operation of taking set differences. And then finally, it must be closed under union. So A3 is the same as R3 in the case of rings. So you can pause this video and try to prove this proposition.